All right, ladies and gentlemen, so I'm going to go through the midterm exam here real quick. Statistical inference is useful for which of the following questions? So what is statistical inference? It's when you take a sample from a population P, and you take a sample from them, and then you make inferences about the population based on what you see in the sample. So a sample of 100 students in Mason is the mean BMI for U.S. college students different than 25. So we have the sample and we have the population. So that one might be it. Using data from the U.S. Census, what is the mean age among men who responded to the census? So if the census is the population, we are not taking a sample from that. If the question was saying what is the mean age among men in the U.S., men in the U.S. would be the population, the census would be the sample, so that one's not it. Using a sample of 100 days, how many of these days? Again, all you have is the sample, you don't have a population here, so again, not it. Using all 17 students in our GCH bio class is a mean height in the class different. So here you have all the students, so the whole population, asking for something about the whole population, so no inference there, you actually are doing the measurement. So number 1 is the correct one. Okay, number 2, which of the following is not a numeric variable? Age in years is numeric because you can go from 0 years to infinity if you want to live forever, but usually in the 70s or 80s here in the US. Number of alcohol beverages. So you can have 0 alcohol beverages, you can have 1, you can have 2, all the way to infinity. So that's numeric. I hope you're not reaching infinity. George Mason's student ID number, the G number. So can somebody have a G number that's 0? Can somebody have an infinite G number? No. Blood pressure in millimeters of mercury. Can somebody have a blood pressure of 0? Yes. If you're dead, you have a blood pressure of 0. Can you have a blood pressure of infinity? Yeah. You can have it pretty high. So out of all of these, the one that is not a numeric variable is C. The other way that you can test for this is, can you add it, subtract it, or divide it? Can I add age? Yeah, 7 years plus 5 years will give me 12 years. Can I add number of beverages consumed? So if I consume 2 beverages and you consume 3, that's 5. Can I add George Mason student numbers? No, that wouldn't make sense, right? My number, G1, 2, 3, 4, 5, plus somebody else's G1, 2, 3, 4, 4. That would not make any sense. Can you add blood pressure in millimeters of mercury? Yes. Somebody has a blood pressure of 120 over 80, and somebody else has and then they take a medication and their blood pressure then is 130 over 90. You can do some math there. All right. So again, this one is the right one. Not that one, not that one, and not that one. All right. And then this question characterizes association between waist circumference and weight. So you have to understand what you're looking at here. The higher the waist circumference, the higher the weight. And we draw a straight line to our numbers here, and if it goes up and to the right, then it is positive. If it were going down and to the right, it would be negative association. If it were flat, flat across, then there would be no association. Okay, so we have a positive association. If they were independent, which is the answer for A, no association here is the same as independent. So that's not it. There is no relationship between waist circumference and height. Again, no association, it would be flat if there were not a relationship. If it would be flat, or the other alternative is that it would be straight up and down, and there would be no relationship there either. Waist circumference had a negatively associated, so I already told you if it was going down and to the right, it would be negative. So the last one, waist circumference and weight are positively associated. So that's your answer right there. Okay, so which is true about confounding? It will not occur as long as our data come from a simple random sample. So remember what I was telling you about confounding. It's when you have X causes Z, But then you have another variable y, which is associated with x and associated with z. So the example that I gave you was coffee and cancer, but then there's smoking. And people who smoke tend to drink more coffee, and they also tend to have higher cancer rates. So when you adjust for your confounder, you find out that it's not the coffee causing the cancer, it's the smoking. So can it happen when the data come from simple random sample? Yeah, if I just go out and simple random sample people who drink coffee, I might still see them getting cancer because I didn't account for them smoking. I didn't ask for them if they were smoking. So that's not the answer. Confounding is a bigger problem in the experimental studies and observational studies. No. It can happen both in both of these, experimental and observational. And it can be a big problem in one and not a problem in the other, or a big problem in the other and not a big problem in the other. We can easily check for confounding by using a scatter plot of our x and y variables. No, actually, if we had a scatter plot, we might still see that association. Coffee drinking here and rate of cancer here. We might still see it. What we would need to do is have two plots. One coffee and cancer in smokers, and coffee and cancer in non-smokers. And what it would look like with confounding is that there is an association, and then there is no association over here, or even a negative association. So not a scatter plot, we would need multiple scatter plots. So then the last answer, it occurs when a variable C is correlated with both the explanatory variable, and the response variable over here. So yes, that's exactly what I described. All right. Okay, so suppose that we take a sample of individuals from Fairfax and determine their incomes. We find that the 65th percentile is 150,000. So think about it this way. 0 percentile, 100 percentile, and here's 65th percentile, and here's the 50th percentile. Okay, and these people are right here. All right, so which of the following best characterizes these data? We should use the mean instead of the median to characterize the center of the distribution, because the distribution is likely skewed and the mean is more robust to outliers. No. The mean is very sensitive to outliers, okay? If somebody has a $1 billion out here somewhere in the 100th percentile, they're going to severely affect the mean. It's the median that is robust to outliers. The distribution of income is likely left skewed because of some extremely high incomes? No. So if we had a lot of high incomes, then there would be more over here on a histogram. And this is a so I think it's left skewed because, okay, so that would be left skewed. All right, so let's say maybe. All right. In our sample, 35% of individuals have incomes greater than 165. So yes, so the difference between 65 and 100 is 35, right? 65 plus 35. So that is true. In our sample, 65% of individuals have incomes greater than, no. So 65% of the incomes are less. So let's answer this question about the skewness. The distribution of income is likely left skewed because of some extremely high incomes. Some, not a lot of them. So this little graph that I made doesn't stand up to that. Okay, so if you had just some extremely high incomes, so if we had our data like this, and let's just try it normally without any skewness. If you had some extremely high incomes over here, if anything, it would skew it to the right, right? Because you would have some out here that we would need to account for beyond the numbers. Not a lot, but some. So that's the answer to that. Okay. All right. Next question, which of the following is not true about normal distribution of every days? So what is this saying? It's a normal distribution. So it looks like a bell. It is centered around 5 with a standard deviation of 10. So it's true that the distribution is centered around 5 It's true that it has a standard deviation of 10. It's true that it's a mean of 5, because that is the mean, that's where it's centered. So we cannot know whether it's symmetric or not. So that is our answer. And so why can't we know? Because we don't know if there's... So in here we could have something like this happening. See how it's a little bit skewed to the left, right? But it's still a bell. And so the way to test for symmetry is to look at the data itself on a histogram. And that's about the only way that you can really look for symmetry. If you have that same number of numbers to the left and to the right of the mean. Okay? And so that is the answer for that. CD4 count is commonly used as a measure of immune suppression related to HIV infection. Suppose we have a sample of 100 individuals whose CD counts are normally distributed with a mean 400. Okay, so normally distributed with a mean of 400. Standard deviation of 40. For an individual, just one person, so my sample size here is 1. With CD4 count of 300, how many standard deviations below the mean of this value? So remember how we calculate that is what we observed. So we observed one individual of 300 minus what we expected. We expected from that bigger sample, we expected 400 divided by the standard deviation, 40. Okay, so 300 minus 400 divided by 40, and that is your answer right there. Some of you might have been tempted to say, oh, well, you need to divide that by square root of n. But what is our n? It's 1. For an individual, that's what the question is. So we could put 1 in there, and then this whole thing here is 1, and then that whole thing is 40. And even if you do put that n of 1 there, it's nowhere in here. You see, that's 10, so that's not it. It's not over here, so that's not it. This is not the answer, because you need to subtract something from that 300 from what you observed, so you know that it's probably C or D. And if it's not that, then it's C. Okay, so pediatricians frequently assess child health using growth charts. Suppose the weight of 2-year-olds are normally distributed with a mean of 30. So normally distributed. So this is being drawn for you right here. That's the mean. A 2-year-old child weighs 36 pounds. What weight percentile is she? So 36 pounds right here. And I actually drew this in R, by the way. So what did we observe? We observed 36. What are we looking for? We're looking for 30, because that's the mean. What is the standard deviation? 2. Do we need to do square root of n? Sure, but I mean, it's going to be 1, because the n is 1. It was just a one child. So that gets canceled out there. So let's see what our answers are. All right, so we saw 36. We were looking for 30 over the standard deviation of 2. So which one is it? All right, so 36 minus 30 over 2, is it 3? So let's do the math. 6 over 2 is equal to 3. So what do we mean by 3? Right? If our sample's here and the child is over here, does 3% make sense? No, right? Because we know that this is all 50%. And we know that this is all some other percent. So 3% is not it. Percentile cannot be determined. No, we can determine that. So that is not the answer. That is not the answer. -3. The answer is not -3. The answer is 3. So that's 3 right there. So that's not it. Percentile 99.9. So yeah, because 99.9 is bigger than 50. So 50, and then we keep going to 99.9. So that child is in the 99.9 percentile, meaning that less than 1% of all children are heavier than that child. That child is pretty heavy. A lot of Halloween candy. All right, 68, 95, 99 rule for normal distributions tells us. So what does it tell us? Don't look at the answers yet. Think in your mind, what does it say? It says that in a normal distribution around a mean, 68% of the observations are going to be within one standard deviation. So that's 68 right there. So blue is equal to 68. It also tells us that 95% of the observations are going to be within two standard deviations. 2SD, 2SD. All right, so red is 95%. So this all big thing is 95%. And then the final thing that it tells us is that within three standard deviations, 3SD, you're going to have 99% of your observations. So black is 99.7%. All right. So what is the answer? The standard deviation must be less than the mean. No, that doesn't make any sense. You can have standard deviations that are really much bigger than the mean. So that's not it. 68% of the observations from a normal distribution fall one standard deviation above the mean. Above the mean. So that would be only looking at the samples that I'm going to draw here in a purple. Above the mean. But no, we said that it's both. It's two means. So that's not it. Okay. 99.7% of observations are normally distributed. Again, that doesn't make any sense. That makes no sense. 95% of observations from a normal distribution fall within two standard deviations of the mean. Yes, it's just like I said. Within two standard deviations, you're going to have 95% of your observations. All right, so that's the answer. So QQ plots. How do you get QQ plots? So let's say that you have your data, and this is the box plot for your data. That's the median. That's the first quartile, the last quartile, right there. And you have all these points along the way. Right? You have all these points here. Boop, 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 boop. And then now you have a normal distribution. This is a normal distribution. Boom, boom. And if you draw it out like this, it'll be like that. It's normal distribution. And you have this other set of points here in purple. Oh, it looks dark blue, but it's purple. And so what you do is that you have your theoretical quartiles coming from here, and you have your sample quartiles coming from over here. So you say my first data point is right here, and my first data point on my theoretical is right here. So I'm going to draw it right there. My second one is here, and my second one is here. So according to their value, you draw it. And if you have a normal distribution of your data, you can see that it's going to be a nice straight line. However, if your data is not normally distributed, and it's kind of skewed, so let's say that it looks like this. Okay, you have more data points concentrated over here. You have some, it's going to spread out a little bit more, and maybe you even have some outliers. So what would that look like if that were the case? So your first value here is pretty low, so down here, and then your first one is normal, so that's right here. So your first point would be right there. And then your second point is pretty low too, so it's going to be right there. Your third is pretty low, but then it picks up, and then it really goes up as you go up this way. So you can see that the line is kind of like that. So again, you're just comparing your theoretical, if you were drawing it from a normal distribution, to the data that you have. Is it left skewed? So if it were left skewed, this data is right skewed, right? So if it were left skewed, let's just draw it out really quick, because I don't want to dwell on this answer too much. This is a very technical thing that you do when you're doing exploratory data analysis. So you guys just need to get the gist of how we draw these plots, not necessarily how to recognize them. I will not penalize you too hard on the final for not recognizing them. So hint for the final. So this one is, kind of low, and it would still be there, but it picks up pretty quickly. So it would actually be like this, and then it flattens out at the end. So it would have to look like this to be left skewed. That's not it. There are no deviations from normality. Well, the fact that it's not straight tells us that there are deviations from normality. So that's not the answer. Sample quartiles are too high at the left and too low at the right, meaning the distribution is too flat. So yeah, that might be. So you see too low at the left, yep, and too high at the right, yep. Too low at the left, too high at the right, not the other way around, not too high at the left and too low at the right. So that's not it. So that's your answer, right there. Okay, let's move on. Statistical inference aims to. So again, remember from question number 1, what is statistical inference? I have a population, I take a sample from it, and then I draw inferences on the population based on my sample. Use a population to draw conclusions about a sample. No, that's backwards. So that's not it. Create confidence intervals for sample statistics. No, that's part of the process, but that's not the aim. Use a sample to draw conclusions about a population. Yes, that's exactly what I just drew. Estimate a sample statistics such as a sample mean. Again, that's part of the process, not part of the aim. There you go. Pretty quick, right? We conduct a survey of HPV uptake and find that 52% of girls aged 12 to 17 have received the first vaccine dose. We find a corresponding 95% confidence interval from 49 to 55, which implies... Now, before you look at the answers, you need to understand what is this 49 to 55. What is it? 95% confidence interval. We are 95% confident that based on our sample, little s, the population... The true number of girls that received the first vaccine dose is somewhere between 49 and 55. We are 95% confident that the true proportion of girls, or the true number of girls, or the true mean, whatever, in the population, based on our sample, is between that number and that number. All right? So it implies that under repeated samples, 95% of the intervals constructed will cover the true population proportion of girls. Okay, so yeah, that kind of is, we'll put a question mark. Because 50% is included within 95% confidence interval, population proportion of 50 vaccine uptake is consistent with our data. Yes. So again, we're 95% confident that the true number is between 49 and 55. If we found that the true number was 50, then that agrees, so that's okay. 99% confidence interval would be wider than 49 to 55. Yes. So remember, we have our mean here, and we have our 95% confidence interval from there to there, but the 99 is a little bit wider, okay? And so I had questions about this one here, but because I already have the 2 out of the 3, then the answer is all of the above. You don't even have to go back and answer that question. All right. Next one. Which of the following is true about the sampling distribution of the sample mean? The sampling distribution of the sample mean. Okay. The central limit theorem. Central limit theorem says that it doesn't matter what my population distribution is like. If my sampling is nice and random, then the means of all those samples will be normally distributed. Right? Around a sample mean. Is the proximity normal, assuming the sample size is large enough? Yes. And the population distribution is not strongly skewed? Yes. So that is your answer. So based on the 60, 95, 99 rule, 95% population means will fall within 2 standard deviations of the... No, it's 95%, 95% not of population means, but of sample means. All right. And then the next question, the next answer... Oh, well. It was cut off, but the answer is this one. So you just have to understand what the central limit theorem. So again, big hint for the final. Question 14, we conduct a hypothesis to see whether the mean number of daily hospitalizations for cardiovascular diseases in Washington, D.C. is different than 10. So we have a population. We don't know what the mean number of daily hospitalizations is. By the way, you don't tell anybody, but you should be using the Poisson distribution because we're looking at counts, but whatever. And we have a sample. We hypothesize that it's HO, that the mean in the population is actually 10, and the alternative is not 10. Which of the following is not a correct characterization of correct decisions? Type 1, type 2 errors. So, what is a type 1 error? And we discussed this in the prep. A type 1 error is when you say that the null is rejected, when in truth it is to be accepted. A type 2 is when the alternative is rejected, when the truth is that it is supposed to be accepted. Okay, so now we know what these are. So a correct decision would occur when we conclude that the mean of which of the following is not a correct characterization of the correct decisions. Okay, not a correct decision. A correct decision would occur when we conclude that the mean number of hospitalizations does not differ from 10, when in reality the mean number of hospitalizations does not differ from 10. So when in reality it's not different, when in reality HO is to be accepted and we reject it, that is a type 1 error. Okay? So that is not a correct decision, so that is not the right answer. A type 1 error would occur when we conclude that the mean number of hospitalizations differs from 10, when in reality the mean number of hospitalizations does not differ from 10. So again, HO is true. And if we reject it, that's the definition of a type 1 error. A type 2 error would occur when we conclude that the mean number of hospitalizations is greater than 10, so HA. We say that is HA. When in reality the mean number of hospitalizations differs from 10. So that's not an error at all. That's the actual, yes, the HA is what we went with, and that's the truth. So that's not an error. Type 2 error would occur when we conclude that the mean number of hospitalizations does not differ from 10. So we're saying that the null hypothesis is correct. When in reality the mean number of hospitalizations differs from 10. When in reality we conclude that the null hypothesis, when in reality the A is the one. So we are accepting the null when the alternative is the reality. So that also seems to be plausible, right? It means the type 2 error would occur when we conclude that the mean number of hospitalizations is not different from 10. That's what we concluded, that HO is true, when in reality the mean number of hospitalizations differs from 10. So in reality, that's what it is. So it looks. Are we rejecting? No. That's the thing. It's when we reject the alternative, but we're not rejecting it. We're just concluding. We're failing to reject the null. So that's not the answer. Okay. We conduct a hypothesis test to see whether the average number of drinks consumed per night for college students is different than 2. Our hypothesis is that null, it's 2. Alternative, it's different than 2. We find a p-value for this test of 0.01. So what is the p-value? The p-value is the probability of a type 1 error, or the probability of rejecting the null when it is true. Okay, remember from the previous one, we rejected the null when in truth it is to not be rejected. So it is 1 in 100 that we will reject the null when it's true. The probability of observing a result as or more extreme is 0.01, giving the null hypothesis is true. Seems plausible. We'll put the probability of accepting the alternative hypothesis is 1 minus. No, we're not talking about that. We're talking about the probability of rejecting the null, which kind of sounds like accepting a hypothesis, but you saw how that got tricky in the first one. The probability of observing a result as or more extreme is 0.01, given the alternative hypothesis is true. Nope, that's not it either. The probability of correctly rejecting the null hypothesis, given the null hypothesis, nope. Not correctly rejecting, but incorrectly rejecting. So answer A. Okay, so answer A there. In a population of hospitalized patients, we are interested in determining whether the mean temperature is different than 37 degrees Celsius. We find 99% confidence interval. So again, what does that say? That within 3 standard deviations, we're going to have 37.1 here and 38.0. We cannot draw any conclusions because we're giving a 99% confidence interval. Nope, we can still draw conclusions there. Because 37 degrees Celsius is not within our 99% confidence interval, in a t-test, we would reject the null hypothesis that mean temperature is equal to 37 degrees among hospitalized patients in favor of the alternative that a mean temperature is different than 37 degrees. Seems plausible. We are 99% confident that the temperature of our patients in our sample are between 37 and 30 degrees Celsius. That is the definition of a confidence interval, right? That the temperature of our patients in our sample, no, that the patients in our population, that's the inference there, so that's not it. Under repeated samples, 99% of sample mean temperatures will fall between 37. Yeah, maybe. So this is saying that if we do no, this is saying 99% of the sample mean temperatures will fall between. So the sample means will be shifting along this. 99% of those. That's not the answer. This is the answer right here. Alpha 0.01 is the one clue. The other one would be, we would reject the null hypothesis that the mean temperature is equal to 37 because 37 is out here. It's outside of, is in a rejection zone, right? Okay, so that's 16. Suppose we are interested in determining whether mean temperature varies by sex. What are the appropriate assumptions for an appropriate t-test? T-test. Remember, for the t-test, independent. Independent sample distribution is symmetric regardless of sample size. And regardless of sample size, all right, we have independence, so that's one of the things. The observations are independent, and for small sample sizes, the population standard deviations are known. Well, the whole thing about the t-test is that if you know the population standard deviation, then you don't do the t-test, right? The t-test is, you do the t-test when your population is really small, and you don't know the standard deviation in the population, your sample is really small, and you don't know. So that is not it. The groups are independent, and the observations are independent. So groups are independent because we have sex, right? And the observations are independent, and the sample distribution is exactly normally distributed. The word exactly, I don't like that there. So the groups are independent. Yes, the observations are independent, and for small sample sizes, the population distribution is approximately normally distributed. So that is your answer right there. So you just have to assume that the population is approximately normally distributed. It doesn't have to be exactly normally distributed. That's why I didn't like that answer there. Okay, so 3 more to go. Consider the following examples. Which example will require applying a paired t-test? So remember, the word paired means that you're sampling a person or a population or whatever before and after. So you give a drug to somebody before, and then you measure their blood pressure before you give them the drug, and then you measure their blood pressure after. So paired means that there's a before and an after component to your sampling. Okay. So in a sample of 20 individuals, vision correction is compared between 2 different contact lens type. Lens A is applied to females and lens B. So no, females and males is not before or after. That's not it. Sample of 20 individuals, vision correction is compared between 2 different contact lens types. Lens A is applied to each individual's right eye, and lens B, nope, not before and after. It's being done at the same time. Sample of 20 individuals, vision correction is compared between 2 different contact lenses. Individuals wear lenses A for 5 weeks, and if they don't have any adverse reactions, they assign to lens A group. That's not it either. Sample 20 individuals, vision correction is compared between 2 different contact lens types. Individuals are randomly assigned to either lens A or lens B. That's not it either. So what did we do wrong here? So pair testing is before and after on the same group. So you're doing it on the same group. So here, females and males, that's not it. Compare between 2 different contact lens types to the right eye, and lenses to the individual's left eye. So that might be the answer there because of that. So what I'm going to do, this is not that one and not that one. So question 18, I'm going to make a note to myself to go ahead and give you all credit for it. If you got it wrong, you get credit. And if you got it right, you got credit. But this is a tricky question. I don't like it because there's no explicit mentioning of the before and the after. It's just saying that they're going to give it to the one eye and to the left eye. It's the same group. It's the same person. It's the same individual. It's the same sample that is being tested twice. So that's the paired part. But I like it to be better worded. So make a note to myself. All right, 19. Suppose we are interested in determining whether mean blood pressure varies by sex. We conduct a 2-sample t-test to test null hypothesis. Mean pressure is the same for females and males against the alternative that it's different. Okay, so HO, the mean blood pressure for men is the same as the mean blood pressure for women. The alternative, it is not. Okay. Test at 17 degrees of freedom. So as soon as you see 17 degrees, go ahead and highlight it in your t-table. Suppose the sample mean for females is 77.2, a sample mean for males is 80.4. It also supposes the standard deviation is 12.6 for females and for males, but the sample size is 6 and 13. So you have everything you need to do the test. So look at your answers. You have everything you need, so that's not the answer. So let's just look SEs. What is the SE? So the SE is everything in the denominator, right? So we're saying that they're not different. So females and males. So females is 6. So females is 6, males is 13. So for females is 77.2 minus males 80.4, right? And then the SE in the bottom is the square root of the standard deviation for females, 12.6. Square that, because we're looking at variance, divided by the n, plus males 23.5, squared again, and divide that by the n. All right. And so that'll give you the standard error. So this is your standard error. So 20, that looks correct there. That looks correct there. That is not correct there. All right. So now we've ruled out D. And then the T statistic. So what is the T statistic? Is what we saw with the female 77.2 minus 80.4 over the standard error here, which is 8.3. So 77.2, 8.4, that checks out, or 8.3, that checks out. So now we have to look at the T statistic right there. So with 17 degrees of freedom, alpha 0.05, right? And because it's not, when it's not equal, we're using a two-tailed. So forget about that. Two-tailed alpha 0.05 right there. So we go down to 2.11. So what is that? What is the 2.11, you might ask? So this is our distribution, right? And we saw, so that's the distribution for females, distribution for males, whatever. But basically it is telling us that that we have a t-value of 2.11, and anything less than that is significant. So the question is the p-value greater than here or greater than that? So the t is there, 95%. So the t-value is less than that, so it's in the or negative if it's 2.11 either way. So the t-value is over here at negative 0.39, but the p-value is what we're looking for. All right, so both of these answers are correct, 18 or 19, because p-value greater than 10 and a p-value greater than 20, then it's the same, right? So if this is 0.10 and this is 0.20, and our p-value is over here, this is true, and this is true. It is greater than that, greater than that. So I'm going to give everybody credit for question number 19 as well. So I did the other question and then this question. And last but not least, question number 20. What is this telling us? It's telling us that the model and the residuals, the probability F, that's what you should look at. How much of the variance is by the model? 16% of the variance is explained by the terms in the model. So we cannot perform an ANOVA on these data because mean writing score is not a categorical. No, you can do, actually you do ANOVA on continuous variables, and that is mean writing score, so that's not the answer. The test statistic for ANOVA model comparing mean writing score across program classes is 70, no, that's the R squared. That's how much of the variance is explained by the model, so that's not it. 0.05, we would reject the null hypothesis in favor of alternative that mean writing score is significantly different between at least two of the three program classes. Yes, and that is what this probability here is telling you. So that is the answer. The null hypothesis for ANOVA model is that mean writing score is the same across program classes. No, the null hypothesis is that the variances, or analysis of variances, is that the variances are the same between the groups. All right, so only that one is correct. Okay, so the extra credit questions, this was pretty open. This is very right skewed here. This one is really right skewed, but because they're both right skewed, then we can probably compare them. And what I was getting you guys to do was to standardize them. So you would take the mean 6.39. That was the expected. What was observed was the number of touchdowns that Warren Moon, he had 33. So the mean minus that, and then you would calculate from the variance. Variance is the standard deviation. The square root of the variance is the standard deviation. So I wanted you to do that, square root of 70.85, and standardize this score to something. And then over here, Patrick Mahomes had 50 touchdowns minus mean 7.99. Square root of 135.89, and that was something else. And I want you to compare these, so you should have standardized them and then compare them to see who stood out. And then you guys gave me some answers, and I accepted them for the most part. Not a lot of you did the Stata command, so which is fine, but you should really learn what those would be. This one. So how do you calculate? You have 6 numbers, so the 6 numbers out of 63, so the probability of the first number is 1 out of 63. But once I take it out, I'm only left with 62, so my probability of the next number is 62, and then 61 on to 1 over, adding 1 over 63, 62, 61, 60, 59, 58, right? But because these numbers, I can pick them in any order, I have to account for that, and I divide everything by 6 factorial, which is 1 times 2 times 3 times 4 times 5 times 6, and that's 720. So the answer is the one that the chances are 1 in 67 million. So that could be it, and that could be it. But this was not a good approach. So that's the answer. Why is it not a good approach? Because it doesn't matter what numbers you draw. You put them all back in together for the next go around the next time. So it doesn't matter that a certain combination of numbers has been drawn. Next time around, there's a good chance, actually, it's a pretty good chance that you might draw the same numbers. So this is how you did the math for that, and then you kind of rationalize that no, it's not a good approach because just because they haven't come up doesn't mean that they're going to come up again. They're independent of previous draws. We talked about this in the prep session, so I'm not going to go through it again. But just know that sample size as it approaches infinity, when n is infinitely great, then SE is infinitely small. Because if you divide SD by an infinite number, then you get an infinite number that approaches 0. You could graph it. So when n from 0 to infinity, and then what is your standard error? So when n is pretty high, when n is pretty low, if n is 1, then the SE equals the standard deviation, if that were 1. And then as it goes along and gets bigger, the standard error gets smaller and approaches 0. Standard error and standard deviation are nearly equal, so that's not it. Standard error is smaller than the standard deviation. Yep. Sample size mentioned the standard error is larger than the standard deviation. Nope. There is no way to determine. No, there is. So that's your answer right there. Standard error is smaller than the standard deviation. Standard deviation is right here. Your standard error keeps getting smaller and smaller. And then question number 4, recently asked to measure a proportion of high school students. So this was actually this is one of my things, and somebody actually suggested that we go to the school. And so no, it's not appropriate. The answer was either that or that. And then if you wanted to discuss it in the discussion section, I would put it here. So it's not appropriate, not because they're health conscious, so you might not sample students who use e-cigarettes in adequate numbers to make your emissions or the smoking status. It's not appropriate because you're not truly doing it at random. That's what I wanted you guys to look for. So that is your correct answer. That's not it. That's not it. That's not it. All right, so that's it. That's the midterm. We'll do a prep session for quiz number 2. You have the instructions for quiz number 3, how it's not going to count against you if you choose not to have it count against you. And then we'll do the final prep. So that's it.